So we are actually on the way about the temperature, pressure, and the pressure effect in a chemical reaction. We have been discussing that if you go with a reaction mechanism, A gives B, then if the energy level at A is actually been increased to a certain level where you can attain an intermediate compound, and this is the minimum energy that required to initiate the reaction. It is called an activation energy. Then later, once you cross this the particular maximum energy that you've been started to initiate the reaction, then it will automatically convert into product. Okay. So if the product energy, what is the potential energy of the product and the potential energy of the reactant, these two might be different, okay, but in some cases it might be same, some cases it will be different. If it's different, then if the potential energy of B is higher than the potential energy of the reactant A, then the product potential energy is high. That means there is some energy it's been absorbed or it's been taken into the reaction to get converted to product. Okay, so if that is the case, then the product will hold some energy within itself. So if that is the case, then it's called an endothermic reaction. And similarly, it is vice versa to the other one. If there is an energy being released from the reactant P, if it converts into product Q, if the energy is being released, then it's an exothermic reaction. So this is what we will represent by delta H. That is what it's called the heat of reaction. Okay, so the standard heat of reaction that we'll calculate it here. But before, if we take an example of A plus, how we calculate this standard heat? So like a standard heat of reaction, for example, you have A of A plus B and B of B, that is A moles of A and B moles of B gives C moles of C plus D moles of D. So if this is the case, then the actual reaction of the actual heat of the reaction will be equal to the sum of the H or delta H of the formation of the reactant. Okay, minus summation of the formation of the product. Sorry. So the formation of the product minus H of the reactant. So this is what it's been represented. If you represent a little more in a detailed form, then we say C delta H C delta H of, okay, this is what we minus A into delta H of capital A plus B into delta H of B. So the total number of moles of the particular reactant into delta the formation. We put formation of D here, formation of A and the formation of B. Okay, this is what you will represent it here. And this summation will be the actual heat of reaction. Okay, but what is the reality in this case is that we take a PFR. PFR. And consider as see how the the temperature and pressure will be here. If you see that V by V naught, that is what your this is what your equation will be. That is C naught integrate XA dXA. In terms of the conversion, I'm writing this here. Okay, if this is the case, then you consider as a first order, for example. You consider A gives B, and it's a first order. K is the rate. This can be written as Ca naught 0 to Xa dXA, and element reaction, then we C naught 1 minus Xa. C naught. Okay, this is okay. How you temperature tau equal to X dx 1 minus Xa. And now you see the K. The K is a very important term here that actually can be written as in terms of exponential of RT. The temperature term is actually involved here. So this is the effect of temperature. So this effect of temperature will directly have an impact in this volume or in the design calculation. Okay, that is what you have to check. That is what you need to calculate. But most of the cases, if you see the reaction, definitely will different conditions. It definitely not at the atmospheric. In if there is any reaction is taking place, then you don't need a reactor here because your space itself a reactor. So you need a reactor to change the condition, to change the parameter so that you can the reactor. We have a direct effect by the temperature. So you need to increase or decrease the temperature. Mostly you will increase the temperature. If you want to increase the temperature, how much you need to increase? How much enthalpy you need to supply? That is what it has been a big question mark here. Okay, so that is what you are going to find it. You check in this chapter. Detailed explanation. I just want to complete the effect of temperature here in detail. So what you will do exactly in a reactor is that you take a reaction path and you always if you like instead of the particular energy which you represent for the reaction path, you put as a temperature here. So you start with the particular temperature T1 and increase the at this point you get the product. So this is the reaction path. Okay, then you cool down to the same temperature level. So this is T2 again, this is T1. So this increases, start from the base temperature. You increase temperature in the reactor, and once the temperature reached at that particular point, then it converts into product, and after it converts into product, you again cool down to a base condition. Okay, this is what happened in the reactor. So how this is going to be correlated here? As you see that, if you take it here in general, the total reaction temperature, okay, for the Sir, இப்போ ஓரளவுக்கு தெரியுதா? கிளார் அடிக்குதா? ரொம்ப கிளார் அடிக்குதோ? இப்படி இருந்தா ஓகேவா இருக்கா? சார் ஏதாவது சொல்லுங்க சார். ஏதோ அஸ்வின் நீங்க சொல்றது எனக்கு புரியல. கொஞ்சம் ஏதாவது மெசேஜ் இருந்தா டைப் பண்ணி விடுங்க. கம்மியா இருக்குமா?
ஆமாங்க சார்.
ஓகே, போர்டில் எழுதிருக்கிறது தெளிவா தெரியலைங்கிறீங்களா அஸ்வின்? சரி, ஓகே. சரி, நான் மறுபடியும் ட்ரை பண்றேன். ஏதாவது இஷ்யூனா மறுபடியும் பேசலாம். ஏன்னா எனக்கு பிளாக்ல ஃபர்ஸ்ட் வந்து பாருங்க. ஓகேவா? In this case, how we write the material balance for the reactor? Okay, that's we will see now. The material balance of the reactor can be written as the total enthalpy of the system, delta H, of the particular position or at the particular temperature. We say delta H1. Okay. The reaction or the reaction. Okay, that is one. This will be that will be equal to total enthalpy of the reactant which is going or the product or solution which is going out of the reactor, and plus the total heat of the reaction or the heat of the formation of the particular the product which is going out. Okay, so this is calculated. H value has to be calculated as with depending on the temperature. So you will write mCp delta T in your heat transfer, right? Similarly here we do agree that we will write as the mCp delta T, but we change the in the for that we you take it at the different temperature T1 to T2 Cp dt, because this one is not the gradient, it is an integral increase because of the change in temperature in the reactor, and again it will drop. So it will increase and it actually decrease. So that's how the design of the reactor has to be. Actual enthalpy balance that you need to calculate it. Okay. So if you substitute this here in this case, so this will be T1 T2 Cp delta T plus dt delta H or H. I'll write it here because it's not clear for you guys. So we can write this, we can say plus delta H R1 equal to, same here, T1 to T2 Cp dust. I will put a dust here because I want to see, show the difference for the inlet and for the outlet. Dt plus delta H R2. So this is how. So then delta H R2 we say equal to delta H R1 plus, you put this together, then T1 T2 delta Cp, because this Cp will be in the delta Cp. Cp dust minus Cp now. Okay. So if this is the case, then the delta plus Cp plus minus Cp. So what is Cp dust now? Cp dust is nothing but the rate, or you can write this as the rate or the heat capacity of the particular reactant, or we say we take it as like E small v G of C plus that C into Cp C plus D into Cpd minus A into Cpa plus B into Cpb. Similarly, what we have done before, it was just a differentiation here. So this differentiation of Cp can be written like this. So this is how the actual heat capacity values will be. And I will give only a last one about how the Cp will have effect. This is nothing but Cp. A. Just give Cpa will be alpha A plus beta into T gamma A into T square. This can go forward. Okay. So like this, if you want to write Cpb equal to alpha B plus beta Bt plus gamma B T square plus like this. So that means the heat capacity have an effect by the temperature. So the heat capacity is nothing but the pressure term where you will calculate from the fugacity, where you keep the pressure at constant pressure. What would be the capacity, the heat capacity of the system that you calculated as in the Cp. So here that have the direct impact by the temperature effect here. So this is what I want to explain here. That means if you want to just temperature reaction. So at final, if you substitute everything inside, at least everything is available in your book. And this has been given very decently and also simple way in the book. So delta HR2 equal to, it's been written as delta HR1 plus delta minus T1 plus delta T1 square, I think, yes. Square plus delta gamma T3 square minus T2 square minus T1 square. Like this. So this is what it's been explained in the way of presentation of heat of the, give the comparisons. Sir, you just don't worry that if it's not clear enough in your video, you definitely go through the book, because in the book it's clearly written. This is a very simple topic. You don't need to be panic here, because you have very simple discussions. This particular unit, you must do one thing here: how the temperature and pressure effect connect to the reactor. Okay. Okay, now I was actually said about the simple rate constant relations here, and the relations in this. But now we will little go into the thermodynamics. We go into thermodynamics now. What is the K value? Have you ever come across an equilibrium constant? Equilibrium constant. It is represented in K. Equilibrium constant, it is nothing but you have a reaction mechanism, for example, A gives R. Reversible reaction product. So if this A gives a product, we say the small k1 and k2. K1 and k2. Small k1 and k2. Okay. If this is the case, then how you relate the K here? The K can be related. I mean, previously we have seen in the reversible reaction, K equal to the equilibrium constant of the reactant, or by the equilibrium concentration of the product. Take a graph, versus time. You start with the A and you go on, and it will stop somewhere, and you start with the R and you go on somewhere and stop. So that means after a certain period, we take it this period, for example, after a certain period, the concentration of A and the concentration of R will be almost same throughout the time. That means the system gets equilibrium. I mean, it actually attain an equilibrium stage. Once if it reaches an equilibrium stage, this ratio will be constant forever. So that is what the K value, that is what the equilibrium constant will be calculated. Okay, that is how the K, the equilibrium K. find out the equilibrium XAE. This can be written. This can be written if you want to expand this. They will expand M plus XAE divided by 1 minus XAE, where M is the C or naught by CA naught. So the K value can be expanded all this. But K value being achieved. So we need to go back towards the Gibbs free energy concept. The Gibbs free energy, where you have the delta G equal to, that is the energy required, equal to delta H minus T into delta S. That is the entropy, and this is the enthalpy. Enthalpy minus the entropy. I mean, it says that increase the enthalpy will pull down, so that how it will get the particular steadiness in the reaction mechanism. Once if you reach a certain point, then you reach a certain free energy stage. Okay, that is what the Gibbs free energy means. So this scale, if you are doing this particular calculation, you might study in your thermodynamics mostly, that you have written as K here. K equal to the activity of the reactant. Okay, so the activity of or we take it A plus B gives C plus D. So in this case, the activity of C, okay, with respect to the volume, I mean the number of moles of power C, with the activity with respect to D, with the power of D divided by activity with respect to A, power of A, and activity with respect to B. So value being activity, but it is about the, as it is nothing but pressure. So are actually being synchronized here. So this activity is nothing but the fugacity or the partial pressure. So we can also write here that K can be represented in terms of partial pressure of the particular component, K of Cc d d. This can be represented in this way too. So that means if you see the Gibbs energy, what could be, how they will write the Gibbs energy is being represented as delta G. Delta G equal to minus or T ln K. So this K is your equilibrium constant. This is what explained, and pressure can be substituted here. The partial pressure can be substituted as the partial pressure into the mole fraction. For example, Y, or the mole fraction Y equal to the capital pressure. So we will put we say here partial pressure. I'll put just the total pressure, PT. Okay. So if you substitute this here in K, you can also write as the Y or C Y D D Y A Y B into the total pressure. So it is the ratio of the mole fraction of the product divided to the reactant total pressure. So this is, and the K also write in terms. So this is, and for yes, you can write it in terms of concentration, that K, we say here Kp. because we put it as a pressure and here we put it as a concentration, then we can write as CR C CD of D by CA of A CB of B. So this is in terms of the concentration. So this is how the rate constant value will be represented. Okay. If you want to relate this to Kc is only in a like it is only the pressure relation here. Okay. Further you can relate. I will write it in a simple way that if you want to relate these two, you can write it Kp equal to Kc RT delta N power delta N. Delta N is nothing but the summation of all the mole fractions. Okay. So this is an another way of the representation, or we can say this is a K value. So, the comparison for the particular equilibrium constant value, that is K. So what are the things actually you need to know that is the equilibrium constant K value. The equilibrium constant K value, either direction, if you go forward with the reaction and backward with the reaction, okay, it will simultaneously occurs on both directions. Okay, and the equilibrium, the chemical equilibrium is actually in a dynamic in nature. So these are the characteristics. So either it will go forward and backward. So there is an equilibrium reactions always, and it is in the dynamic in nature. And if the system is at equilibrium, property will be constant at that particular stage. Or the property of the system will become constant. It does not change if the equilibrium is reached. Okay, if the system reaches the equilibrium, then the property of the system constant. That means you need to wait until the reaction get reach at the equilibrium. Okay, so then you can calculate the property. If you want to change the equilibrium, the direction can be changing the temperature and the pressure effect. And in another case, you can use catalyst, but the catalyst does not change in its position of the equilibrium of the forward and the backward. Speed up the equilibrium because put a graph like. We take a time and we take a concentration. We start with A, R here, and this, and R comes like this. So this is the equilibrium, right? Stages. So at this point, you will reach the constant, or we say at this point. So at this point, you reach the equilibrium. But if you have a catalyst, so what will happen is that it will try to speed up the reaction mechanism. You see? The same thing, but it will attain here. So it will be little more early. So this is what will be done by the catalyst. It will speed up the equilibrium state, but it does not change the property of the system. Okay, these are the characteristics in the equilibrium. conditions in a reaction mechanism. So this is what you need to know. You need to learn from this particular subject. You need to understand here. With this, I just stopped today because we have two more topic, that is adiabatic and non-adiabatic, that we need to discuss. How to calculate the conversion rate for the adiabatic operation and how to calculate the conversion for the non-adiabatic calculation. Condition. If you know these two conditions, then this chapter is almost finished. Okay. So next week we will try to finish as much, but I don't know whether if it does not work out, we need to go with the special classes for some classes extra. Okay. Wow. Ajit, தெளிவா தான் இருக்கீங்க. Right. Super. Sir, Mr.